Record to the cloud. I will not record to the cloud. How dare you? Is that the best you can do? Optimize. All right, here we go. What is optimization? What comes to mind when you hear that word, optimization? Because when you hear that, something comes to mind. I mean, everyone has different things when they hear optimization. There's different connotations and things that come along with that. But what is optimization? Like, you have things that come to mind. You have your own connotations, but what is the definition of it? So I went to Google to find out. The condition of being optimized. It's like, freaking Google. Like, how are you just gonna like throw that at me? But I mean, that's fair. Like, Google's just a trolley troll. But they happen at behind their trolley trollness, there was a little bit more. So optimize is to make the best or most effective use of a situation, opportunity, or a resource. In math, it's a technique for finding a maximum or minimum value of a function, given sets of constraints. Wait a minute, maximum or minimum value? We know how to do that. That's just checking critical points of derivatives. By the way, optimize comes from optimus and eyes. Putting those two together gets you optimize. So it's from Latin, it's really like best eyes. So that's my favorite way to say optimize right now, is to say best eyes. So optimization is bestization, something like that. I had a K. Words are hard. I don't try them very hard. I never found a use for English after high school. So, but anyways, I must have to point this out, that in Transformers, Optimus Prime is literally best prime. Fun fact. So, by the way, if you didn't notice it from what I just said, I'm pointing out yet again. When you find Extrema, you are doing optimization. So we've been doing optimization for a little while. So really, today's not adding anything that different. It's just pointing out how we can do it with word problems. That's basically today's lesson. So I'm going to show you 2 word problems. As long as you kind of follow along, you're going to be a good place. So here's the situation. The volume of an open-top rectangular box is 4,500 cubic centimeters. The length of the rectangular base of the box is twice the width. What height will make the surface area as small as possible? This last sentence is what makes this optimization, because we're trying to find what makes it as small as possible, which, hey, that's one of those words that is minimum. So we need an equation to start working with. And again, we're trying to find a minimum of the surface area. So that's something to think about. Now, when I start a situation problem like this, whenever it's a word problem, I try to draw a picture. Hey, there's my picture. You can tell that it's not a really good box because a lot of the lines aren't connected, but hey, whatever. That's fine. That's a 2020 box. And then, yep. And now what I'm going to do is I'm going to label that box with some different pieces of information. Because, it's nice to see some different things every now and then. And I am going to move this. Sorry, it's a lot different working on one screen versus like 3 screens. It's much more weird. All right, there we go. Move things around. All right. So now that I move things around and everything's like a fifth of the size that I normally deal with it at, that's fine. We have a picture drawn. So I'm going to start like labeling things that I recognize and know. Oh, it helps if I click back on the screen. So I know the length is twice the width because that was right in the second sentence there. I also see mentions of volume and surface area. So I should probably write an equation for volume and for surface area. So what should I do first? I did volume first. So after realizing that the length is 2W, the volume equation should be 4,500 equals 2W times H, which, I mean, that's just multiply, multiply, multiply. Ain't too shabby. Surface area, there's 5 rectangular sides to this box because there isn't a top. So there they are. That is all the sides. Because let's see, 2W times W is the base. And then the other ones are the two sides. And that's why there's a 2 times in each front of them. All right. Well, ideally, what we'd like to do to find a surface area as small as possible is really want to find a derivative of this. Because as W changes, or as H changes, like the volume is going to, the surface area is going to move around a little bit. And as the volume moves around, as those dimensions move around, the surface area is going to change. So really, at some point, the rate of change is going to be 0, which will give us a maximum or minimum. But we need to get rid of one of the extra variables here. By the way, before we even do that, let's clean those two equations up a little bit, just so that they look more condensed and less like all over the place. So there's a volume and surface area. I really want to work on this surface area equation. I look at this one, I'm like, I almost could take the derivative of this one, but it has 3 variables in it. I've got W, H, and surface area. It'd be nice if I could get rid of one of those variables. I think I can get rid of H by using the volume equation. So I'm going to solve the volume equation for H. Now that I have that, I can combine the surface area and volume equations together. That volume equation is going to help constrain the surface area so that I can actually find a maximum or minimum. Bam! There's a substitution. So right in the parentheses is the H. That's what H is equal to. So now I'm going to plug it in there. Let's simplify that a little bit so it looks a little easier to play with. All right, there we are. Now, as you see that surface area equation, you can see that there's only one variable on one side and one variable on the other. Hey, friggin' sweet. That means I can easily take a derivative and not have to worry about a whole bunch of different things. So I made a mistake as I wrote this next thing. It should be d over dw, and I did d over dx. So bear with me, apologies. It's more of a pain in the ass. I didn't know if you could hear the screaming kids or not. That's super awesome. That's the fun part. That is actually the best. I'm really happy that you can hear them. See, I mean, it's all part of the birthday gift I'm giving you. Because I don't know how many screaming kids you have. I think we only have 4 kids out there today. I think one of the sisters is gone. So I think we have just the 5. I think they just messed with the door a little bit too. Who knows? There might be a random kid coming in. We'll find out. Anyways, back to what I was thinking about. This derivative of the surface area equation gives me this bad boy over here. Again, it says d over dx. It should be d over dw. I goofed, and it was too much of a pain in the butt to go back and change that to dw because I had to recreate the picture and then put it back in the correct sequence of animations. And I'm like, nope, that's way too much work. I'm just going to curate that, Sun Gun. So there you go, curation. Now that I have this surface area, the derivative of the surface area equation, what I'd really like is to set that equal to 0 and solve for w, because that's going to give me the critical points. When I was doing the work for this morning, I'm like, I don't want to show all that algebra. I'm just going to graph it. So I did. And look, when you graph the derivative, and this is the derivative right there, it's 0 at that one point, at 15, 0. It's not 0 anywhere else, but it's 0 there. Notice it's negative beforehand, positive after. Hey, negative to positive. That's a minimum. Sweet. That's what we wanted. We want to make the surface area as small as possible. Bam. Oh, that's interesting. I was like, I'm pointing at the screen. Why can't you see my finger? I'm doing really great today, if you haven't figured that out. So that's the point that I needed. But I want to know the height, not just the width, because W is equal to 15. But what's the height? 20. So when W is 15, H is 20. Boom. There's one of them. What time is it? Oh, sweet. I got 10 minutes. Hot diggity damn. I'm found for that. All right. Here is the algebra. I was just going to leave that up and then take some things out. I'm like, nah, I'm just going to redo this. But there's my handwriting out. As you can see, derivatives. Hell yeah. I'm all about those derivatives, bro. Anyways, there's the algebra if you want to see how I solved for W to be 15, you can totally do it. There it is. Ain't too bad. It's just multiply both sides by W squared to get rid of the W to the negative second, and boom, done. It was good to go. Hey, here's another situation. Farmer Jin Zhou has 300 feet of fencing to enclose 2 identical rectangular pens that share a common fence. What are the dimensions that will yield the largest area? Do you have a question?
Hey.
Hey.
Are you synchronous right now? Or?
Yeah.
Okay, never mind.
Okay. I just had to ask if I was currently synchronous. And it's recording, so it's even better. Anyways, what are the dimensions that will yield the largest area? So again, just keep throwing Optimus up there because I think Optimus just needs to be around more. I should draw a picture. Hey, that looks like a nice picture. Honestly, it looks like a domino. I guess. Basically a domino. That's what this thing is. But there's, again, 2 identical rectangular pens that share a common fence. What's the dimensions that will yield the largest area? Well, I should probably label some dimensions on here. So A is that vertical dimension. B is the entire horizontal length. I could have let B just be like the horizontal length of one of the 2 stalls. That felt like it was a pain in the butt to say, so I'm just like, let's let B be the entire thing. Sick. So we got that. Now let's write some equations. I'm going to play dominoes because that's what they use in kindergarten to teach counting and numbers. So I'm going to go print some dominoes out later, and I'm going to post them up on our window, and we're going to have sight numbers in addition to sight words. Anyways, oh, I should flip these 2 around. But area, that's not supposed to be volume, that's area. Man, I didn't even recognize that when we went through last hour and no one called me out. I was like, oh, it's totally volume. It's not volume, that's area. Gall darn AL cohort, no one called me out. I'm being wrong about that. All right, well, V is going to represent area because it's 2020. And V is an upside down A without the bar holding it together. So really it's A that's falling apart on its head. So it really is, again, 2020. Anyways, here's my area equation that literally no one called me out on last hour, which is even funnier because I'm pretty sure I just said volume, volume, volume the whole time because I see V. Anyways, there's my area equation. It's just literally A times B. The problem with that is I want to find the largest area, and I'm like, I don't know. How do I know what's the largest area? I can just do A and B. There's nothing like holding it back. The perimeter equation is helping me out because I don't know how much you know about fencing. I'm assuming you don't really know what fences are because no one does. But fencing goes around things. Fun facts. So fences go around things. And if they go around things, that means they're perimeter. Oh my gosh. So that's how I can use the 300 feet of fencing for a perimeter equation because fences go around stuff. Kidneys right there. So I have my 2 equations. Really, I want to make this is the one that I want to find the derivative of so I can do something with it. But I need to get rid of one of the variables. So I decided A was the one to be to disappear. Why did I pick that one? Because I was like, hey, that sounds fine. I had a better joke with it last time. It didn't come off as well this time. Whatever, that's fine. Anyways, so I have that. So now I'm going to take that and plug it in for A and see what I get. Boom. I plugged it in for A. Now I'm going to simplify that. Hey, look. It is a whole lot of coffee. I'm actually like have my travel mug with me today instead of just a regular giant cup, which is even better because this is like one of those ones that keep things like super hot or the temperature for a long period of time. So like when I drink it, it's still like it's relatively fresh out of the pot of coffee. Great. Yeah, because normally by this point of the day when I'm drinking coffee, if I still have some left, strangely, it is room temperature at best, especially downstairs. But in that, I'm like, hey, it's still at least lukewarm. That's pretty decent. I'm pretty happy with that. So that's where I'm at right now. Also, again, I don't know. That's probably that. Anyways, moving on. Volume. No, not volume. Area. So now I want to take the derivative of that so I can find the largest area. I'm looking for an extrema there. So the derivative is that. Again, I made a mistake. It should be d over db, not d over dt, but I goofed, made a mistake. I've made some major mistakes. Whatever. Y'all understand and go with that. I think it's important that you see I make mistakes because I ain't perfect. I don't expect you to be perfect. I just expect that we all keep learning and growing together. All right. So now let's set it equal to 0 and solve. This didn't take that many steps, so I decided to show you algebra here. Boom, I got B. Cool. But I'm not done because I'm looking for the dimensions. I wanted to know what A and B are. Boom. And I plug B back into this equation for A up here, and I'm good to go. There's my answers. 75 equals B, 50 equals A. Bam. Here's a little picture I drew, and here's someone's work. Can I read whose that is? Nope, there are no names on there. So that was someone's work. In class, we would have just spent the whole day working on just these two problems, and I'd be coming around giving you tips as you were working on them, but well, whatevs. So that's some work along with that. I hesitate in giving you steps to do stuff like this because I like you coming up with your own steps, and then we can talk about them later and discuss the validity and how good they are. But I decided I'm going to share with you my heuristics. These are things I do for optimization. Again, by being heuristics and just general steps, you don't need to follow them every single time. But if you're looking for a general process to generally help you through stuff, cool, here you go. Here's how I wrote them out. The book writes it a little bit differently, and I'm going to show you that in just a moment. So I write equations, then draw a picture. Then I solve one of the equations for a variable, usually the one that has probably only two variables in it. I solve for one to plug it into the other one. So substitute into the equation that's going to be optimized because you're going to be told, I want the least of this or the most of this. And that's how you can start figuring that out. Then do a derivative. And then we're going to find critical points, AKAs. We're going to set the derivative equal to 0, just in case you're still not sure about that vocab term, critical point. And then I'm going to solve that. Then I'm going to wrap up the problem with a pretty bow, because you need to wrap it up with a pretty bow. Because you can just solve, but you have to make sure you're actually answering the problem. Like in this one, boom, this is step 6. Like I set the derivative, found the derivative, set equal to 0, and solved. But I wasn't done because I didn't answer the question. What are the dimensions that will yield the largest area? Need to answer that. And if we go back, man, there's a lot of animation. This one asks, what was the height? Again, I could have just stopped here when W is 15, but that's not answering my question. My question is, what's the height? Which is why I had to wrap it up with a pretty bow. Bow? I don't know how to make a bow. I don't know. I can't figure it out. Should have thought about it ahead of time. Rip. So yeah, here's the books. The book pretty much outlines this for you. It's also in there, so you can check it out. The big thing that they talk about that I want to make sure I mention is identify the constraint equation. What that means is one of the two equations that you write, or one of the equations you write, like holds back, allowing for optimization of the second equation that you really want. So going back, in this problem, the perimeter equation is my constraint equation, because once I solve that for a variable and plug it into volume, it constrains the volume so I can find a max or a min. And if we go back yet further to this one, the volume's the constraint equation because I know the volume has to be 4,500. But the surface area is not constrained, but that's the one I'm trying to optimize. In this case, find the minimum for. And that's it. Let's do soonish. Probably do next week. We'll probably do another problem on Friday when I'm back downstairs in my general place of learning with my 1, 2, 3 monitors. That I paid. No, I guess I paid for that one. Whatever. Anyways, I enjoy my setup downstairs. So there's that. Let's do soonish. Again, 33 is an optional one. If you're feeling lucky, try those, work on those, do the best you can. We'll probably start chapter 4 at some point next week. I don't know if we're going to do a quiz, a summative quiz first or after, or right at the end of right before break. I'd rather just do it right after 3.7. We might do a little review first. I don't really know yet. I'll let you know once I know more. Mr. Reema and I are just trying to be on the same page about things, and we haven't talked much more about other than what we're going to do this week. So we're going to keep working and talking about that. What else do I want to say?
Are most recent quizzes going to be unlocked today?
It should be. I have to double check. When I looked yesterday, there were 3 people who hadn't finished it. I know at least one person finished it. I got to check to see the other 2 did. If everybody in both classes have finished it, I'll unlock the answers and let you know. Yeah, and we'll talk from there. But initial results, things look pretty good when I first last looked. So I'll let you know, but I'll unlock the results. And we'll probably talk about those on Friday in addition to doing another problem or something. I think that's what I have for you.
Have a great birthday, Dudeski.
Hey, thanks. That's all I got for today. Woo! All right. Thanks for coming. We'll talk to you later.